So in vectors, you guys also learned about projections. So when a vector is broken into a pair of components, we already know that that's rewritten as a projection of the vector onto the x and y axis. So for example, when we have this blue vector, xi, yj, xi is the projection of a onto the x-axis and yj is the projection of a onto the y-axis. However, we don't always need to necessarily project vectors onto the horizontal or vertical axis. You can actually just project them onto any other vector we want. So for example, here we can project this blue vector onto this black vector here, and our projection will be this red vector. So the way to visualize a projection is sort of just think of the projection as sort of the shadow of the vector. So for example, just imagine you're shining a torch on the vector. The shadow here is the projection of this vector onto the other vector. And the way we notate the projection of A onto B is we have projection of A onto B like that, with B in subscript like so. So the formula we use to find the vector projection is if we have a vector and we're projecting onto here, if this is the angle between, so this is B and this is A, the length here we know is going to be magnitude of A cos theta using trigonometry. So that will counter for the length. But in order to get the direction, to make sure it's not just a length that's going anywhere, like it could be the same length, but it could be going in any direction. In order to make sure that it's going in the same direction as B, we're going to multiply it with the unit vector of B. So that is in the same direction as B, but with a magnitude of this result here. However, this formula is a pure formula. It's the one where a projection formula comes from. But it's not always the easiest to plug numbers into this formula because you might not always know the angle between the vectors. So using some manipulation, we could also get these other results, which this one is the most common one, which you will be definitely using at school. And it comes from the dot product. We know that the dot product of A and B is magnitude of A and B multiplied together times the angle between them. So therefore, we can rearrange and we can say that magnitude of A times cos theta is equal to the dot product of A and B divided by magnitude of B. So if we plug that into this form here, our projection of A onto B will simply just be, this will become dot product of A and B over magnitude of B. And we know that the unit vector of B we get by dividing B with its own magnitude. So therefore, this thing will become dot product of A and B, magnitude of B squared times B, like that. And the magnitude of B squared is just going to be the dot product of B with itself, like so. And that's how we get this formula, which you'll see at school. Comes from this pure formula, but just with the dot product rearranged to make it into an easier form to use. So here's sort of a standard E1, E2 level question you might be asked in an exam. What is the vector projection of A onto B? So remember that projection of, so basically here we got -1, -2, so this is A, and -4, -3. So yeah, so we're basically finding this projection here onto B. So projection of A onto B, we said, is dot product of A with B over dot product of B with itself times the vector B. So here, dot product of A with B is going to be -1 times -4 plus -2 times -3. And dot product of B with itself is -4 squared plus -3 squared. And that's all multiplied with -4i minus 3j. So this will give us, will be 4 plus 6 over 16 plus 9. Yeah, 4 plus, so negative 4i minus 3j. So this will be 10 over 25, which is 2 over 5. Negative 4i minus 3j. And this will give us negative 8 over 5i minus 6 over 5j. And that is your vector projection of A onto B.